Good afternoon, everybody. Can you hear me?
Good
Yes, sir,
afternoon.
you are audible. Yes, sir.
Can you see my screen?
Yes, sir.
Oh, so let's begin. Let's review what we did last time on a new topic which we started last time, that was open maps. The first thing we talked about was compactification of a topological space, and we gave some examples. The open interval 0, 1 has this compactification. But it also has another compactification, this one. And then we showed that the projection from a space to a point is proper. If it's proper, then X is compact. And gave two proofs under two different assumptions. First assumption was that X has a compactification. Second assumption was, well, okay, we only gave a proof under this assumption. Now, this is true more generally, but we will not prove it, will not need it. It's an exercise given to you. Conversely, we proved that if X is compact, then the projection from X cross Y to Y is a closed map. Again, we proved it under some assumptions. First assumption was for metric spaces. And second assumption was that Y has a compactification. So there were two different proofs under these two assumptions. Then we defined a locally compact Hausdorff space. All spaces for us henceforth are Hausdorff. Unless I see it, I'll keep on reminding you though. And when we make new spaces, therefore we'll have to prove whether they are Hausdorff. Then we introduced the definition of locally compact spaces. We looked at examples and non-examples, including C01 was a non-example. And then we gave the construction of something called a one-point compactification of a space. And then we asked what is one-point compactification of a real line or of R2. And somebody, one of you, replied correctly how the sphere is a one-point compactification of R2 under stereographic projection. Similarly, Sn for Rn. I don't think we proved this. I don't think we proved this. I don't think we proved it. We ran, and I don't think we defined phi product. We ran out of time. So let's come to today. We'll revise some of those things, of course. So our spaces will be Hausdorff, as I said, and a compactification. A compactification is an inclusion of X as an embedding into something X prime where X prime is compact. We are even more pleased when this is open, which we will see we can always have when X is locally compact. And so last time we talked of various examples of compactifications. Now, a locally compact Hausdorff space, remember the definition goes like this. This is X. And suppose you are given a point X. This is X. Now, suppose you are given some neighborhood. So, U, X belongs to U and U is contained in X. This is some open neighborhood. then what we demand is inside that open neighborhood, there should exist some compact set C. And inside that compact set, there should be another open neighborhood. So what we are demanding is between X, okay, between X and X, first of all, you are given this U. So we are demanding that there should exist some neighborhood. So this was U, this was V. There should exist some neighborhood V, which is contained in a compact set C, which is contained in a neighborhood. So V is open in X. Is open in X. And this is compact. So what is given? X, U, and X are given. V and C must exist. So therefore what happens is, given any point and any neighborhood, inside that is a smaller neighborhood which is contained in a compact set which is contained in the larger neighborhood. Okay. This in particular means that I could have taken V to be the closure of I could have taken C to be the closure of V. Okay. So is the definition of a locally compact Hausdorff space clear? Yeah, any questions on this point about the definition of a locally compact Hausdorff space? None. Very good. So last time we also talked about why C01 is not locally compact. You see, I'm going to give you an example. Look at the functions sine of n times x. If nx equal to, this is a bounded sequence. In sup norm. In fact, the norm, what is the norm of any Fn? Tell me. Well, at least for large enough n. I don't know what is norm of the very first one. Does it reach its top pi by 2? No, pi by 2 is still greater than 1. Okay. So this is equal to what? Bolo.
So supremum of mod of Fnx, x belongs to closed 0, 1.
What is it?
1.
1. At least for n greater than or equal to 2 at least. The very first one, you see, goes like this. Sine, you know, the way it goes, it reaches the value 1 at what? Pi by 2, na? So pi by 2 is still greater than 1. So the very first one doesn't reach the value 1, but all the succeeding ones do. All the succeeding ones do. So this is a bounded sequence, but this has no convergent subsequence. Exercise. I think you should now take the more advanced point of view where your teacher doesn't have to say the word exercise. When some statement is made without showing you the full proof, that is an exercise for you. Okay. Therefore, in your tutorial, you should tell the tutor that, yeah, we have been given lots of exercises. Here are some. And I'll make lots and lots of statements, which I'll say them in a very persuasive manner, but may not give you the full proof. And then you should be skeptical and prove everything. And that is exercise. So this kind of active study, when you, every time there's a definition, you give yourself 3 examples and 3 non-examples, then one doesn't have to write a new exercise. Every time there's a proof, you try varying the argument a bit and see what happens. See where each condition is used, what happens if you drop one of the conditions, and that is exercise. So exercise is something which you give yourself instead of being directed by somebody who says, hey, do this. You have to be self-directed in your study. Okay. So this has no convergent subsequence, exercise. Okay. Now let's define proper maps, which we defined. Today is the 3rd time we are defining it. Okay. The definition is a map X to Y. When do you say this is proper? When you take X cross Z and map to Y cross Z, should be closed. Closed map should be a closed map for all Z. Okay. Proper means, this is the definition of proper map. Map is proper if every such change of base, this is the base, this is the top, I have changed the base. And what is this vertical map here? Can somebody tell me what map we are talking about and where is it sending small x and small z? Yeah, tell me.
F cross ID.
Small x and small z is going where?
Fx and Z.
There, and not ID. No? Okay. This is the map. And as you rightly use the word ID, this map should be called F cross identity of Z. This map should be closed for every Z. Okay. So now, if I tell you that this should happen for every Z, every topological space Z, okay, what are the topological spaces that you will try? What are the most obvious topological spaces you will think about when you start thinking topology? 2 answers. One, follow.
Points in Sierpinski space.
The what word? Say it loudly.
Points, the first one.
Yes.
And the second one, perhaps the Sierpinski space.
No. Empty space and point. These are the 2 obvious objects of the category of topological space, the initial and terminal object. Try them out. So if I take Z to be the empty space, is the resulting map closed? See, even in our 6th week, we are back to empty set.
Yes.
Yes. Why? What is
Yes.
that map? Empty space to empty space. Any space cross empty space is empty. Is that clear to everybody now? By now? The product consists of ordered pairs. First element has to be in X, second element has to be in Z. But if Z is empty space, there is no chance of having any second element. So it has no elements. Therefore, X cross empty set is always empty. Okay. So empty set to empty set, why is the map closed? Because the only closed subset of the empty set is empty set itself, and its image is the empty set which is closed. That's why. But next is the more interesting one. As Ishan said, take Z to be a point. So what happens if I take Z to be a point?
Get that the map is closed because X cross point is homeomorphic to X, Y cross point is.
Correct. Correct. So this in particular shows that every proper map is closed. Okay. Take Z to be a singleton point. The singleton point is our name for a space which has exactly one element in it. Sometimes that space itself is called this. Now, is the converse true? Is every closed map proper? And on the very first time we talked about proper maps, I gave you an example of a map which was closed but not proper. Do you recall a map which is closed but not proper?
Yeah, reals to point.
No, sorry?
Real numbers to point, R to point.
Correct, correct. And what was the geometric picture you have to remember? What is the geometric figure we used?
The hyperbola projecting down.
The hyperbola projecting to x-axis. Correct. So converse is not true because as now you have imbibed the lesson, I am happy that you take x to be equal to r. And now you take z also to be r. And you take y to be point. In that case, here you will get r cross r to r, and the two coordinates are called x and z, and send them to z. Now in this, we'll draw the z-axis here and the x-axis here, and we will consider the closed subset, red colored closed subset, defined by the equation xy equal to 1. Because xy is a continuous function on R2, xy equal to 1 is a closed subset. It's a closed subset of R2C. It has no limit points outside it. And its projection, what is its projection? Its projection misses out on this point. This point is not there in the projection. All the rest is the projection. Okay? So image of hyperbola equal to R star contained in R. Not closed. So is the hyperbola example clear to everybody that how real numbers to a point is not proper even though it is closed? So proper is something stronger than closed, because with the example of a single point, we saw that proper map is closed. And with this example, we saw that there are closed maps that are not proper. Now here's my next question to you. So suppose I have two composable maps. I have x to y and y g z. Suppose this is proper, and suppose this is proper. Then is the composite map proper?
Yes, sir. Because if you take, sorry?
Yeah, prove it.
Okay, so if you take X cross A to Z cross A, that factors through Y cross A.
So now take the product of this whole diagram with A, as you called your space. Funny name for a space, but why not? Okay. So the simple claim we are making is G cross identity A composed with F cross identity A is GOF cross identity A. Let's check it, what it does to a point here. Any point here looks like X A. Where does it go under F cross identity? to fx-A. And where does it go? So this gets mapped here. And where does this get mapped to? GFX cross A. So this combined map is nothing but G composite F cross identity. Okay. Now I claim that this is closed. Why?
Because if it's proper.
Correct. Who answered this?
Arnab sir.
Arnab, you are right. This is closed because F is proper. And this is closed because G is proper. Now, final point, composition of two closed maps is closed. Why? Begin with a closed set. Under the first closed map, its image is closed, and under the second closed map, that closed image goes to another closed set, which is the image under the composite. So this we have proved. Any doubts about this proof? I'll wait a few seconds. If you have doubts, please ask bravely. Okay, there are no doubts. In that case, let me ask you the following question. Question. If f from x to y is proper and z any space, then is f cross identity z from x cross z to y cross z proper?
Sir, I think it is.
You are right, Arnab. Why do you think?
Because we can take Z cross W.
Yes. So Arnab, you have in mind the following equality. X cross Z. Now I take further product with W. And take the map to. But this is equal to X cross Z cross W. Equal to means a certain obvious homeomorphism, right? And so this map, this is Y cross Z cross W. This map which we want to be closed is actually this map X cross Y cross, to wipe it and make it look clean. Y cross Z cross W is Y cross Z cross W. So this map is closed because x to y is proper, and I am taking the product with z cross w. Z cross w is my new space. You may call it A or whatever. And so therefore this map is just a single product of the original map with a new space. New space is made from z and w is z cross w. Okay. So answer of this is yes. Yes. And this is the proof for that. Proof. Okay. So is there any doubt on this point? So let us come to the next point of proper maps. So now suppose I have space Y. Here's Y. And here's X. And X goes and sits inside as a closed subspace here. This is the inclusion. My question is F proper? What do you think?
Yes, sir.
And why?
Sir, because if we'll take any closed set to a closed set and like.
You are telling me this map is closed. I am asking you whether it is proper.
So we are given F is closed, no?
F is a closed embedding, but now why is it proper? So you have to take product with something, no?
Yes, and the product, like for the product, it will be mapped identical.
This product map Y cross A is again a closed embedding. See, if X is a closed subspace of Y, then X cross A is a closed subspace of Y cross A. That's all that I'm saying. Okay, na?
Yes, sir.
Therefore, every closed embedding is proper. So in a Hausdorff space, any point going sitting inside a space is proper map. Okay. Now comes the next question. So suppose F from X to Y is a proper map and Z is a subspace of Y. Then is the induced map F restricted to F inverse Z from F inverse Z to Z? Is this proper? Let me draw a picture. So there is X. It's going down to Y. So here's Y. Here's X. And now inside Y, I have some closed subspace. Sorry, inside Y, I have some subspace. I don't care what. I have some subspace Z. This is Z. And I take its inverse image here. This is F inverse Z. And I take the map from here to here. So if this is proper, is this proper? So this is a, yeah, this is proper. Then is this proper? What do you think? Should I leave it as an exercise? Show it is proper. If X to Y is proper, and I restrict my attention to some Z inside Y and take its inverse image, that is also proper. Yeah, will you guys do it as an exercise? Okay.
Yes, sir.
Yes, you. Arnam is willing to do it as an exercise. I hope everybody else will also try. Then these are the statements I proved to you yesterday. If X to point is proper and if X admits a compactification, then X is compact. Let me remind you of the proof because the proof is very nice. So this is X. And this is point. Suppose X has a compactification, and that compactification, let me call X prime. This is a compactification. So then I take X prime. This is my X prime. Inside X prime, there is X. This is X. X sits inside X prime, and X prime is compact. To show X prime is compact, I'll psychologically help you by writing it like as if it looks like a closed interval. This is compact. Now I take the product. The product looks like this. While I must take these sides to be black. These sides are black. Okay. Every fiber is a copy of X, right? And now what I'm going to take is, see, X only goes from here to here. From here to here. So I am going to take the diagonal. This is the diagonal. Okay. This diagonal, diagonal. Yeah, Arnav, you remember very well, this is the set of all XX. Okay. Now, my claim is so all our spaces are Hausdorff, remember all the time. Okay. So this is closed. This is closed as X is Hausdorff. So it's closed here, but it can't have any further limit point here either. This I'll leave to you to check. Okay, remember all our spaces are Hausdorff, and this will remain closed. You see, where can it have a limit point? My X has to tend to something, which means, and that has to tend to something in X cross X prime. Think of metric spaces. That means there's a sequence of xn's converging to some X prime. But then where will the first component converge? Which means that X prime better be in X itself. So this is closed. Now, what is the image? This is the projection. This is the projection. This point, let's call phi, the projection of all of X to a point. Then this is phi cross identity of X prime, which means the projection on X prime. Projection P2, which sends X comma X prime goes to X prime. This is the projection. So what is the image of the diagonal under this second projection? Bolo. What is the image of the diagonal?
That is X sitting inside
X prime. Wonderful.
X
Very
prime.
good. So image of this, image of P2 equal to X sitting inside X prime. And saying that this X to a point is proper amounts to saying that this map is closed for every such any factor you take X cross A to A. And therefore this is closed. Therefore closed. So now I have a compact space and I have closed subspace. So finally we invoke the property that we always know, namely closed subspace of a compact space is compact. Therefore, X is compact. So we have proved this. Yeah. So again a pause. Tell me whether you have any questions. No. Looks like you have none. Now my next claim is if X is compact and if Y admits a compactification, then X cross Y to Y is a closed map. So let's take it. I have X to Y. Y admits a compactification Y prime. Okay. And so I have X cross Y to Y. This is the projection. Sorry, not X to Y. X cross Y to Y. This is the projection on the second factor. I want to show this is a closed map. This map, second projection. And I am assuming X is compact. So Y sits inside Y prime. Okay. As a subspace, and this is compact. And so this goes and sits inside X cross Y prime. Is, and this is the second projection again, is this map closed? Bolo. Is this map closed? And remember, all our spaces are Hausdorff. Yeah, it is closed. Why is it closed?
Take a closed subset of the upper space, the X cross Y prime.
Yes.
That's compact. It
Right.
comes down to Y prime, so it's
Right.
compact in Y prime.
Right.
And Y prime is Hausdorff because it's a compactification.
Correct.
So it's closed.
So Ishan, you are right. So P2, we'll have to, let's call it P2 prime to distinguish it from P2. Is this map P2 prime? So yes. And therefore P2 is closed. This is something we talked of a bit before, that if I have closed map and if I take something inside and take the inverse image, if this map is closed, then this map is closed. So this map is closed, so this map is closed. And so any compact space to point is proper, because given any compact space to a point, take product with any space Y, and the projection is closed. And when I said any space Y, I am just now confining my attention to spaces which are compactifiable, Hausdorff spaces, etc. But as I keep telling you, you don't need these assumptions.
So, but
yeah,
isn't every space compactif? Doesn't every space have a compactification?
That's what I don't want to get into.
Okay. Sorry.
And the reason why I don't want to get into is also something that I explained to you last lecture. I said that in your first exposure to topology, think of metric spaces as much as you can. You can think of convergence of sequences. You can think of closed sets in terms of limits. You can imagine balls inside open sets. Let your imagination work with the help of metric spaces. There are spaces which are not metric spaces, but for this kind of topology that we are doing, metric spaces is all that matters. Now, for a general topological spaces, representing convergence by sequences is not possible. You can make a kind of definition that some space is first countable and then still use sequences, but then not all spaces are first countable. So there is alternative technology, more advanced one, called nets, filters, etc., which you will find in general topology textbooks, which can deal with the situation. So if I want to do all this stuff without assuming compactifiability straight away, then I'll have to invoke that kind of technology, which I don't want to, because it will distract us away from our geometric purpose, for which metrizable spaces are good enough. Okay. So now we have proved that X to a point is proper if and only if X is compact. The two halves took place in statement 9. Okay. What is this called? Statement 11 and statement 12. I started using Roman numerals, and I wrote 1, 2, 3, but after that I struggled. I couldn't remember how to go on writing on and on Roman numerals, but then I figured out and here it is. Okay, so this means 12. So statements 11 and 12 tell you that a space is compact if and only if projection to a point is proper. Now let us come to one-point compactification of a locally compact Hausdorff space. So always locally compact means Hausdorff for us. I keep repeating myself today all the time that for us everything here is Hausdorff. Actually the terminology changed around 1950s and has not reached textbooks, definitely has not reached the kind of popular textbooks used in MSc, that compact means compact Hausdorff. While if an open cover has always a finite subcover, such a space is called quasi-compact, Q-U-A-S-I. The Americans will call it quasi, rest of the world will call it quasi. So a quasi-compact space is one in which every open cover admits a finite subcover. And so locally compact means locally compact Hausdorff in the old terminology. Okay, now let us, but you stick to the old terminology because in your MSc examination and for the kind of examiners that you will most probably meet, the terminology has to be the old one. Now, we defined a one-point compactification of a locally compact Hausdorff space. So I want to ask you, okay, for some examples. If X is the empty space, okay, so compactification, we gave it that notation, that star was the extra point. So if X was the empty space, then the one-point compactification X star was equal to what? Hello.
The singleton.
The singleton, correct. And you see that this is indeed compact. This is compact. Hausdorff, locally compact. And empty is open in singleton. Okay, next. Suppose X itself was singleton. Okay, X itself was a point. Let me call that point A. Then X star was what? Chalo, bolo, answer.
I'm not sure about this, but will such a thing exist? A one-point compactification?
Is that Ishan?
Yeah.
Yeah, Ishan, think. Yes, it exists.
Okay, because the thing is, okay, maybe I'm missing something.
So good I asked this question, see. There is an art of asking questions to students, and it involves putting the teacher has to imagine what a student might misunderstand or understand, and therefore design a question which will get a wicket. And this is my favorite sport. I enjoy devising questions which get wickets. Okay, so what is it?
So is it A itself?
No, again. So think.
The doubleton with discrete.
Yes, the extra point. The extra point is B. This is the star. Okay, this is discrete. So again, low compact, locally
Isolated.
compact, blah, 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 blah. Yeah, is that okay? Are you guys convinced that the answer is okay? Not
Can I
difficult,
ask
no?
why I thought that this? Can I ask where? Can I
Yes,
get?
sure. Ask.
Yeah.
Ask. Yes.
I thought the space had to not be compact from the onset, because
Yeah. Why did you think so?
when you're embedding X as a dense subset of X star, the point
Nowhere
can.
did we say it is dense, see?
Okay, then I thought compactifications was dense. Okay,
No, let's
okay.
go back. Is it dense anywhere?
Okay, sorry. The definition wasn't there of exactly what a
Correct.
compactification was. So I thought dense, which is why.
A compactification is another space such that there is a subspace there and that space is compact. One point compactification is where that space has one extra point.
Okay, I had a different definition. That's why I asked.
And so you see what will happen, Ishan, with your definition is you won't get a functor, right?
Yes.
With your definition, a functor won't be possible.
Okay, so could you please define compactification, because I knew something was a problem. I didn't know there was a
that was
solution.
defined right at the beginning, that a compactification is, this is compact house dog, this is a compactification. This is an embedding. Yeah.
Okay, all right. So this, okay, all right. Thank you very much. Thank you.
Yeah. You also see the need for having an extra point to make it nice and functorial.
Yeah.
Yeah?
Okay.
What is it functorial in? That we will soon see. It is functorial in locally compact spaces and proper maps. Okay. We will soon see that. Okay. So, okay, let's give some more examples. Suppose X was interval, then X star equal to, bolo.
S1.
Correct. That is the circle. And this point is the extra point. And you may say, you might take 0 to 360 if you want. And so this is 0 degrees to 360 degrees instead of 0 to 1. You can reparameterize the interval. And so this is the interval and this is the extra point. Okay. Again, this space which has come out is compact, Hausdorff, locally compact, and interval is open in it. Okay. Open in it. Perhaps you will be happier if I call that interval 0 to 2 pi. I don't know. Radians are the favorite in colleges. Though in your algebra class, degrees are better, right? Am I making sense to you why degrees are better in your algebra class than radians? In your Galois theory, you will study what angles are constructible and what not. And those angles are easier to describe in degrees rather than radians. So when you study your Galois theory, you will see that. Okay. So this example is also clear. So Oh, let me once again remind to you the general recipe. The general recipe, general construction. So I take my x. This is my x. And I want to make, how to make x star. And I x into x star. I want to put x inside it. How to make. Okay. So you take any compact subset. So here's a compact subset. Here's another compact subset. Here's yet another compact subset. Okay. So these are compact subsets. Compact subsets. And X is locally compact. I keep reminding you Hausdorff. So there are plenty of such compact subsets, lots of colorful things. Now, I, as a set, take X star to be X disjoint union one singleton point, which I'll call star. And I'll stop writing these brackets when I get bored of writing them. Topology. One, all open subsets of X, and you put X inside there as this component. This is the X. All open subsets of X are declared to be open in X star. In particular, X is open in X star. Okay, but now you want some open neighborhoods of the point star, which is to be thought of as point at infinity. This is the whole idea. This extra point is point at infinity. So I want to know what are its neighborhoods. So an open neighborhood of star is any X minus C union star where C is compact in X. Okay. And now, because we want all various rules to be satisfied, third thing you do is take arbitrary unions, finite intersections of the above. Probably intersection is not going to produce anything really new. Unions will. So you understood what is this topological space? I have given you a basis, so to say, and take the topology generated by these things. Okay, and
Hello,
that
sir.
is our. Hello, yeah. Bolo.
Sir, is the singleton star
Uh,
is open in the topology of X star?
Thank you, Arnav, for your question. So let's observe.
I can
Let's
take the
answer.
empty set and then empty set.
What is the complement of empty set? Will be all of x star, na?
Yes.
Because x minus empty is x, and you have added this star to it, so you get x star. So x star is of course open. But what is interesting to take is observation. If x is already compact,
Oh, then x minus
then
x.
star is open in x star, and conversely. And conversely, because x star is indeed compact. So in fact, we will prove that for this construction, the theorem to be proved is theorem x star is compact Hausdorff and locally compact. And I x into x star is an open subspace. So because this is compact, this is indeed compact because of this, see the theorem here. This is compact, and if this is open, then I remove an open set from a compact set. What remains is a closed set. And a closed set in a compact set is compact, therefore x will be compact. So I want all of you to try and write a proof of this. It's very easy pictorially. Okay. What is the neighborhood of infinity? Everything far away. So suppose x was R2, then for your compact sets, you will take bigger and bigger balls. And their complement are smaller and smaller neighborhoods of infinity. You understand? What is a neighborhood of infinity? Complement of a compact set. How to make a smaller neighborhood of infinity? Take a bigger compact set and take its complement. That's a smaller neighborhood of infinity. Now you should be able to prove that this is compact Hausdorff and locally compact, assuming x is locally compact Hausdorff. And so this is something which you please sit down and attempt, because I have run out of time to show you the proof. And so tomorrow we'll talk about the proof and still some, so again locally compact Hausdorff and whatnot. In fact, this whole theorem. What other statement? The other statement is saying that if x and y are locally compact Hausdorff, then x to y is proper if and only the inverse image in x of each compact subset of x is compact. This is a wonderful statement because this gives you a very intuitive feel for checking what maps are compact. The definition is very nice based on a universal property, but as usual with universal properties, how do you go around checking whether a given map is indeed proper? So if these are locally compact Hausdorff spaces, you try to see whether the inverse image of each compact subset is compact. And then you are home. And if these spaces are Rm and Rn, that means since the inverse image of closed set is closed and compact are bounded and closed, so it will only amount to saying that the inverse image of a bounded set is bounded. See, very nice. It becomes very nice compactness for maps between Euclidean spaces, and we'll exploit it. Next time we may give a new proof, new meaning, new to you guys, of the fundamental theorem, of that C is algebraically closed a proof which was invented by my teacher, Professor M.S. Narasimhan. So I'll tell you this proof based on proper maps next time. So आज का खेल खत्म हो गया और कोई सवाल है तो पूछिए, चलो।